What specific problem does the proposed method address in the realm of long chain of thought reasoning capabilities in LLMs?
The proposed method addresses the inherent unreliability and difficulty in controlling emergent reasoning behaviors in large language models, LLMs, which can lead to inconsistent manifestations of advanced reasoning capabilities like long chain of thought, COT reasoning. By explicitly aligning LLMs with three domain general reasoning meta-abilities, deduction, induction, and abduction, the method aims to enhance the model's reasoning skills in a structured manner. This alignment is operationalized through a task suite designed to train and validate these meta-abilities, ensuring that performance improvements reflect genuine reasoning skill acquisition rather than mere memorization. The approach also demonstrates that aggregating predictions from models aligned to individual meta-abilities can significantly boost overall accuracy, thereby addressing the limitations of relying solely on emergent behaviors. Ultimately, the method raises the performance ceiling for LLMs in reasoning tasks, making them more predictable and scalable.
How does the proposed method work? Illustrate step by step how the three meta-ability tasks, deduction, induction, abduction, are constructed and utilized in training the models.
The proposed method involves a three-stage training process that integrates the three meta-abilities, deduction, induction, and abduction. First, in the meta-abilities alignment stage, each meta-ability is trained independently using specific tasks. Deduction is assessed through propositional satisfiability tasks, induction through masked sequence completion, and abduction via reverse rule graph search. Each task is designed to ensure a clear separation of reasoning types, allowing the model to learn distinct reasoning skills effectively. Next, in the parameter space merging stage, the models trained on each meta-ability are combined by linearly interpolating their parameters, which allows the merged model to retain the complementary strengths of each specialist. Finally, in the domain-specific reinforcement learning training stage, the merged model undergoes further fine-tuning using domain-specific data, enhancing its performance on tasks such as math, coding, and science. This structured approach not only improves generalization across domains, but also raises the performance ceiling of the model significantly.
Can you provide a simple yet illustrative example showing how a model performs a deduction task using the propositional satisfiability framework outlined in the paper?
In the deduction task, using the propositional satisfiability framework, the model is presented with a set of logical rules and a candidate hypothesis. For example, consider the rules. If it rains, then the ground is wet, R1, and it is raining, R2, with the hypothesis being the ground is wet, H. The model must verify whether the observation, O, follows from the premises, R1 and R2. It does this by proposing a truth assignment for the variables involved, systematically deriving consequences from the premises and checking for contradictions. If the model finds that the hypothesis logically follows from the premises, it returns a satisfying truth assignment. Otherwise, it reports that the clauses are unsatisfiable, demonstrating the core structure of deductive reasoning as outlined in the paper.
What are the theoretical or practical benefits of employing this meta-ability alignment method over traditional instruction tuning in terms of performance and reasoning capabilities?
The meta-ability alignment method offers significant theoretical and practical benefits over traditional instruction tuning by enhancing reasoning capabilities and overall performance. Specifically, aligning models with deduction, induction, and abduction allows for the development of complementary reasoning skills, which leads to an average accuracy improvement of over 10% compared to a vanilla instruction-tuned baseline. This method also enables the models to generalize better across various domains, as evidenced by consistent performance gains on unseen benchmarks, with the merged model achieving A3. 5% improvement in overall average scores. Furthermore, resuming domain-specific reinforcement learning from a meta-ability checkpoint raises the performance ceiling, with notable gains in math tasks, indicating that the foundational reasoning skills instilled through meta-ability alignment significantly enhance the model's adaptability and effectiveness in complex problem-solving scenarios. Overall, this approach not only improves accuracy but also fosters a more robust reasoning framework, making it a superior alternative to traditional instruction tuning.
How is the effectiveness of the proposed method validated in the experiments? What specific datasets, metrics, and benchmarks are used to assess its performance?
The effectiveness of the proposed method is validated through a series of experiments that utilize a curated task suite aligned with three reasoning meta-abilities: deduction, induction, and abduction. The models are evaluated on 7 benchmarks from math, coding, and science domains, including Math 500, AMY 1983 to 2024, and Live Codebench. Performance metrics include pass at 1 results for most benchmarks, while average accuracy, average at 3.2, is reported for AMY 2024 and AMC 2023, computed over multiple samples per problem. The experiments demonstrate that the merged model consistently outperforms instruction-tuned baselines, with significant gains in overall accuracy, particularly in math tasks, where the merged model shows an improvement of 3.5% on the overall average and a 4% gain on the math average. Additionally, the results indicate that the proposed alignment strategy enhances generalization capabilities, as evidenced by the model's performance on unseen benchmarks.
What are the key results obtained with the new method across different benchmarks? And what do these results indicate about the model's reasoning abilities and generalization?
The key results obtained with the new method indicate significant improvements in reasoning abilities across various benchmarks. For the 7B model, the induction-aligned model achieved an average improvement of 1.7%, while the deduction-aligned model provided a notable 2.8% increase on the Math 500 task. The integration of all three meta-abilities in the merged model further enhanced performance, raising the overall score by 2.5%. In the 32B model, each aligned model surpassed the Quen 2.5 to 32B instruct baseline, yielding a mean gain of 3.1% on the math overall metric and a 4% gain on the math average. These results demonstrate that the proposed alignment strategy not only instills robust reasoning skills, but also ensures reliable generalization beyond the training domain, as evidenced by the substantial performance gains across unseen benchmarks.